Okay, consider something like this. Let's say this is a rough surface and a block is placed on it. It's a rough horizontal surface. Means the entire surface is at the same level from the ground, same level above the ground. Assume this block is given some speed and released. What will happen to the block?
After a point, it'll stop.
Okay, it slows down and eventually it will stop. Correct. What makes it stop? Means which force makes it stop? Friction from the rough surface. Correct. Now, the block was initially moving, so it had some kinetic energy, right? Finally, it comes to rest. Final velocity becomes 0. So, initial kinetic energy is non-zero. Final kinetic energy becomes 0. Okay. And it's moving horizontally. There is no change in its height above the ground. Therefore, whatever was its initial potential energy, let's call it as U, the final gravitational potential energy also must have been U, because it is neither taken higher nor brought lower. Okay, its height from the ground remains the same. So there's no change in its potential energy, but there's a change in its kinetic energy. Can one of you quickly recollect what is mechanical energy of a system?
That is the kinetic energy plus the.
It's the sum of kinetic and potential energies.
Yes,
Correct.
sir.
Initially, it had both kinetic plus potential energy. Finally, it only has the same amount of potential energy as it initially had. So tell me, in this process, is mechanical energy lost, gained, or doesn't change?
That it's lost.
Obviously, it's lost. Let's say it had an initial kinetic energy of some 20 joules, an initial potential energy of 100 joules, then its total mechanical energy initially is 120 joules. Finally, that kinetic energy is gone. Potential energy remains the same. Can one of you tell me why potential energy remains the same? Gravitational potential energy. Why is it not changing? Because gravitational potential energy changes when the height of an object from the ground changes. Delta U is mg delta h. Now this object is moving horizontally. Its height above the ground is neither increasing nor decreasing. So it maintains the same amount of potential energy. So final mechanical energy 0 plus 100 is 100 joules. Therefore, mechanical energy is lost. Now, if there is a change in mechanical energy, whether it's a gain or a loss, some non-conservative force must have been doing work. And in this process, as one of you already answered, the non-conservative force involved is friction. And tell me, as the block slides forward, would friction have done positive work or negative work?
Negative work, sir.
Negative work. Object is moving in the forward direction, force is in the backward direction. F dot S becomes negative. Friction did negative work. Friction is a non-conservative force. We even proved that. Therefore, the mechanical energy of the system decreased. Okay. Fine. So gravity is one of the conservative forces that we have talked about. What is the other conservative force we had discussed?
Spring force.
Spring force. And for every conservative force, you can associate a potential energy. So springs also can store potential energy. That is what I had given in the last worksheet. And the potential energy that a spring stores is called elastic potential energy. A spring, a rubber band, sponge ball, okay, they all store the same kind of potential energy. It's called elastic potential energy. In case of a spring, the formula will be half k x square. Okay. I had sent you a worksheet with the derivation in it. Do it and send it back to me if you have not done already. But if you solve it step by step, you will get this result. You will find out that the potential energy stored in a stretched or a compressed spring, okay, stretched or a compressed spring, is half k x square, where as usual, k is the spring constant or the stiffness of the spring, and x is the deformation in the spring. It could be compression or elongation. Fine. And this formula also suggests that if x is 0, means if the spring is neither stretched nor compressed, if it's at natural length, it does not store any potential energy. Fine. So remember, the formula for gravitational potential energy is mgh, or in fact, change in gravitational potential energy is mg delta h. And spring's potential energy, the potential energy stored in a stretched or a compressed spring, is half k x square. Okay. For now, we'll be dealing with these two kinds of potential energies. Right. Now, last class, I think we had solved one question where a block was released, block connected to a spring was released when the spring is at its natural length. This question. So when the spring was at natural length, we connected a block to it and released. When spring is at natural length, spring does not exert any force, but weight of the block will be acting and it will pull the block down. So you are asked to find out the speed of the block when it comes to equilibrium position, and equilibrium elongation is mg by k. So when it comes down by that distance, what speed would the block have? That was the question. Can one of you tell me the idea we used to solve that problem? Which concept in physics did we use to solve that problem? It's there on the screen itself. What is the idea we used to get the speed of the block?
Sir, the work done by the weight and plus the work done by the spring force, and then we
So the
equate it, and then
concept,
we.
that means the concept used is work kinetic energy theorem. Work done by all forces is equal to the change in its kinetic energy. That's one way to solve it. Let us solve it in a slightly different manner now. Which method to use in exams? It is your, I mean, you will have to decide whichever you are comfortable with. Now we know that work done by all forces is equal to the change in kinetic energy of the system. We have proved this also. Okay. And this is always valid. There are no exceptions to this. Okay. Suppose work done by all the forces, suppose this is only by conservative forces. Fine. That means the work done by non-conservative forces is zero in a particular situation. So all the work done is done by conservative forces only. Then, okay, we have introduced a condition here. Under this condition, delta W by definition becomes negative of change in potential energy, because delta U, change in potential energy, is negative of work done by conservative forces. Now, if all the work is done only by conservative forces, then that work should be negative of change in potential energy. And work done is always equal to change in kinetic energy. Therefore, send the negative delta U that side. Delta U plus delta K, K means Ke, kinetic energy, becomes 0. Change in potential energy plus change in kinetic energy is change in mechanical energy. That becomes 0. That means initial mechanical energy of the system is equal to the final mechanical energy. Okay. This is what we call as conservation of mechanical energy. And condition we had discussed in the last class itself. Non-conservative forces should not be doing any work. Okay. Or the total work done should not include work done by non-conservative forces. Then mechanical energy is conserved. And this is proof. So law of conservation of mechanical energy can be derived from work kinetic energy theorem. How? Work kinetic energy theorem proves that work done by all forces on a system is equal to the change in kinetic energy of the system. And if the work done by all forces put together is the work done only by conservative forces, then the left hand side becomes negative of change in potential energy. And then you send it to the right hand side. Change in potential plus kinetic energies becomes zero. That means change in mechanical energy is zero. Now, how do we apply this? Initial mechanical energy is equal to final mechanical energy, means initial potential energy plus kinetic energy is equal to final potential energy plus kinetic energy. Okay, listen carefully. You should get the thought, no, like when to apply mechanical energy conservation. One of you tell me, on what factors generally does potential energy depend? Pawan, you tell.
Sir, height.
Uh, See, we discussed two types of potential energy now. What are the two types of potential energy? What are the two conservative forces that we learned till now? What are the two conservative forces that we learned about?
Sir, I don't know.
Okay, anyone?
అంటే లేట్ వచ్చాను.
ఈరోజు కాదు, లాస్ట్ క్లాస్లో డిస్కస్ చేసినాం. Okay, anyone else? What are the two conservative forces that we had learnt about?
Sir, spring force and gravitation.
Gravity and spring force. For every conservative force, there is a potential energy associated. So if we had learnt about two conservative forces, then we'll have to consider two potential energies from now onwards. Now, what Pawan said, potential energy depends on height, is related to gravitational potential energy. Change in gravitational potential energy is mg into change in height. Okay. What is the formula for spring potential energy? Note this down, all of you. I don't know if you have derived it using the worksheet or not, but note this down. Potential energy stored in a spring, half kx square. Okay. Now we were discussing when to apply mechanical energy conservation. And I asked you the question, on what factors does potential energy generally depend? Potential energy depends on arrangement of a system. It could be earth and a mass system. It could be spring block system. It could be two blocks connected to a single spring. Okay, whatever it is. It depends on, like, potential energy changes if you change the arrangement of a system. And kinetic energy depends on speed of parts of the system. Therefore, when you will apply mechanical energy conservation is when a system undergoes a change in its arrangement. And speeds of the objects change during the process. In such cases, you can try to apply mechanical energy conservation if you are sure that total work done is only the work done by conservative forces. Mechanical energy conservation comes with a condition. Fine. So this class and over the next few classes, we'll be discussing and we'll be applying mechanical energy conservation. We'll be discussing how to do it and we'll be applying it. Okay. Let's consider a much simpler problem first. Last class question was slightly difficult. Let's consider those spring block questions. Maybe this one. Yeah. Work done by the spring force as the spring returns to its natural length is how much? Fine. Let me copy the diagram. Initially, the spring is compressed by 10 centimeters. And let's take the answer also. Answer we got is 4 joules. Okay. And that 4 joules is nothing but work done by the spring force. And based on that, we got speed of the block as 2 meters per second. Fine. Let's solve this same question in a different way now. That day we solved it using work energy theorem. Work done by all forces is equal to change in kinetic energy. Okay, let me remind you the situation. On a spring block system is on a smooth horizontal surface, and this dotted line represents the natural length of the spring. The block was pushed to the left by 10 centimeters, so the spring is compressed by 10 centimeters, and we release the block. The block moves to the right because of spring force acting on it. And as the spring relaxes, it exerts lesser and lesser force, but it will exert a force till it comes to natural length. And under the influence of that force, the block would have gained some velocity by the time it comes here. That velocity is what you are asked to calculate. Okay. So look at the system. It's a spring and a block. It was initially compressed and it is relaxing. So basically the arrangement of the system is changing. And arrangement of the system is changing, speeds are changing, speed of the block is changing, and you are asked to calculate the speed of the block. So based on the change in arrangement, means from what initial state to what final state it is going. Based on the change in arrangement, you have to calculate the speed. This is an ideal case where you'll apply mechanical energy conservation. Because mechanical energy conservation involves these things only: potential energy, kinetic energy, change in arrangement, and speeds. Fine. So when you look at a situation like this, it should strike you that maybe mechanical energy conservation is applicable. But there are some factors to be considered. Mechanical energy conservation comes with a condition. One of you tell me, not one of you, let me ask. Saket, you tell, as the block moves to the right from position A to position B, what forces act on it? What all forces act on it?
Sir, the spring force.
Okay, one obvious force acting on it is the spring force. Then
Gravitational force, normal force.
weight will be acting on it and normal force will be acting on it. Correct. We are trying to find out the speed of the block by using mechanical energy conservation. Saket, can you tell the condition for conservation of mechanical energy?
Sir, the arrangement needs to change.
No, arrangement is changing. Mechanical energy, when is it conserved? Okay, anyone? What is the condition for conservation of mechanical energy? See, in the name itself, the condition is there. Conservation of mechanical energy. And mechanical energy will be conserved by conservative forces. Conservative force. That's why they are called conservative forces. So the condition for conservation of mechanical energy is that work done by non-conservative forces should be zero. Okay, if non-conservative forces don't do any work, mechanical energy won't be disturbed. Fine. Now, I'll give you all a minute. Think about it. As the block moves from A to B, okay, I'll ask the answer, but think about it. Which of these forces will do work? Okay. Saket, you only tell which of these forces does work as the block moves from A to B.
Sir, wait. Sorry, sir. Spring force.
Spring force. What about weight and normal? Will any of them do any work?
No, sir.
No. Why is work done by weight 0?
Sir, because they are on the same level. They are not like moving up and down. So they are in a linear phase.
Okay. See, you can just say force and displacement are perpendicular. Weight acts this way, displacement is this way. Force is perpendicular to displacement, so the work done is 0. What about work done by normal? Why is that 0?
So same reason.
Same reason. Okay. So these forces are acting on the block, but they are not doing any work. Spring force is the only force doing work. And one of you quickly tell me, is spring force conservative or non-conservative?
Conservative.
Conservative. Therefore, mechanical energy conservation can be used to solve this problem, can be applied in this problem. Okay. Fine. How do we apply mechanical energy conservation? How do we apply any conservation law? Initial value of that quantity is equal to final value of that quantity. So you can say initial potential energy plus kinetic energy of the system should be equal to final potential energy plus kinetic energy of the system. That's how you apply mechanical energy conservation. And the conservative force doing work here is only the spring force. So the potential energy which you must write in this equation is the potential energy stored in the spring. And as I said, the formula for potential energy stored in the spring is half k x square. Therefore, you will be applying mechanical energy conservation this way. Half k initial compression or elongation in the spring squared plus kinetic energy initially. Now spring is a massless system, massless object. So spring won't have kinetic energy, block will have kinetic energy. Because kinetic energy requires mass, half mv square, it depends on the mass. Spring is moving, spring is stretching, so particles of the spring are moving, but they are massless. So spring itself won't have kinetic energy, the block will have. So you'll write half m initial velocity squared, that's for the block, is equal to final potential energy also is of the spring only, so half k final deformation squared plus half m final speed squared. Okay. Now I want you all to apply this, substitute the values in this and derive the speed of the block. And be careful with the initial compression of the spring. It's given in centimeters, but all other terms are in meters, are in SI units. So you convert this to meters first, and then you substitute in the equation. Solve it quickly. Your aim is to calculate the final speed of the block. Type your answers in chat. Any answer?
So 1 meter per second.
Okay, you got it as 1. Let's see. The other day, the answer we got is 2 meters per second. We'll see. Aishwarya, can you tell the values we substituted? How much is K?
200.
K is 200. Is that what you substituted?
Yes.
Okay. Initial compression or elongation?
So 0.1 the whole square.
10 centimeters is 0.1 meter and you square it. Okay, that's half K xi square plus half mass of the block I think is 2 kg. U square is 0. It was released from rest is equal to, finally, we want to calculate the speed of the block when the spring returns to natural length. So how much is x final?
0.
0 plus half mass of the block is 2 kg v square. Okay. We can cancel all the halves. And this term is 0 anyway. This term is also 0. On the left hand side, you have 200 into 0.1 whole square is 0.01. So that becomes 2 is equal to 2v square. Okay, you get v as 1 meter per second. Fine. The other day we got it as, let's just go back and look at the solution once. How did we get 2 here? Just a moment. Work done by spring force is integral kx dx with proper limits we did. Okay, we took initial limit wrong there. Fine. The limit I took 0.2, like initial compression, I took it as 0.2, means I took 20 centimeters. Or maybe, yeah, it was given as 20 only, I think. But as it changes, it becomes 10 at one instant. That's what we had considered. Okay, fine. Initial compression was 20. Okay, not 10. While explaining the solution, I think at one moment I wrote it is 10 and then it becomes 9.8. Okay. So let's make that adjustment in today's problem. For today's problem, this is the answer. Okay, 1 meter per second is correct. But had the initial compression in the spring been 20 centimeters, okay, had x initial been 20 centimeters, then you would have written 0.2 whole squared here, in which case it would have become, the answer would have changed to 4, okay, wait, 200 into 0.04, that is 8. So left hand side becomes 8. Right hand side becomes 2v square. In that case, you would have gotten v square is equal to 4 and v would have become 2 meter per second as we got the other day. Okay, fine. But see, none of you came up with an answer. What difficulties were you facing in substituting in this equation? Pawan, why were you not able to give an answer? Okay, just a moment. Saket, you tell me, where were you stuck?
Sir, when it came to X final, I could not.
X final is the final deformation in the spring. I told you, no, you have to find the speed of the block when the spring comes to natural length. Natural length means final deformation is 0. Okay. Yusuf, what about you? Why were you not able to give an answer?
The X final and X initial, I didn't know what to substitute where.
Okay, fine. But you observe that we got the same answer that we got in the last class. So,
Yes, sir.
yeah, I'm telling this to everyone. So basically, the arrangement of the system is changing. Some parts are moving there. The way they are moving is changing. The speed of the block is changing. So in such situations, you will check if mechanical energy conservation is applicable. And if the conditions are satisfied, you can apply. Okay. Now let's try the question we solved in the last class. This one. Okay, I'll explain the situation to you once again. So there's a vertically suspended, means hanging spring block system. It is suspended from a rigid support. And okay, you know what is going to happen and all. So when the spring was at its natural length, a block was attached to it and released. And at natural length, spring doesn't exert force, block experiences weight, so it starts moving down. At some point, as the block starts moving down, spring force starts acting in the upward direction, weight acts in the downward direction. Then at some point, weight of the block gets balanced by the spring force. When the spring is stretched enough, spring force balances weight, and that happens when the elongation in the spring is mg by k. Kx should become equal to mg, so x should be mg by k. We know this. Okay, it's written there. Fine. By then, the block would have gained some velocity. The problem was to calculate that velocity. And what is the answer we got in the last class? We used work kinetic energy theorem and we got the speed as g root m by k. Okay, let's see if the same thing can be derived using mechanical energy conservation. So here also, you know the initial state of a system and the final state of a system. Some objects are moving and speeds are changing. Objects are moving, speeds are changing. In such cases, you will try to apply mechanical energy conservation. Fine. Pawan, tell me, condition for mechanical energy conservation.
Sir, initial and final must be equal.
Yeah, that is not the condition. That is the equation. When is
Okay,
mechanical energy?
Non-conservative forces must be equal to 0.
Okay, see, let's be clear here. Non-conservative forces need not be 0. Like in the previous case, normal force on the block is not 0, it's acting. Okay, there is a normal force acting this way. The work done by them should be 0. Okay, just to be clear. I'm telling this to all of you. Work done by non-conservative forces should be 0. Then mechanical energy of a system does not change. Fine. Pawan, you only tell me, when the block is released from position A and it goes to position B, during that displacement, what all forces act on the block?
The spring and gravitational.
Force exerted by the spring and the weight of the block, gravitational. Okay. Only two forces are acting, that's fine. Now tell me, which of these forces do work? Will the spring force do any work on the block or not?
Yes, sir, it will.
Yes, because spring is vertical, so spring force will be vertical. Block is also moving vertically. So spring force does work. Will gravity do any work or not?
Yes, sir.
Yes. Gravity is also vertical, displacement is vertical. So this time both forces will be doing work. And if two conservative forces are doing work, we'll have to include two potential energies in our equation. Okay, that's what makes this problem like the next level problem compared to the previous one. Okay, let's see. Spring force is conservative. Weight is also conservative. So all the forces doing work are conservative in nature. Therefore, we can conclude that mechanical energy conservation is applicable in this case. Let us apply it now. And how is it done? Initial mechanical energy, that means initial potential energy plus kinetic energy, is equal to final potential energy plus kinetic energy. And this time, since there are two conservative forces doing work, two potential energy should be considered. So we write potential energy of the spring initially, or spring potential energy initially, plus gravitational potential energy initial plus kinetic energy initial is equal to spring potential energy final plus gravitational potential energy final plus final kinetic energy. The equation gets a little lengthier. Okay. Now we know how to write potential energy in a spring, we'll do that. We know how to write kinetic energy also. Gravitational potential energy may create a small problem here. Listen, all of you. So far, we have only discussed the formula for change in gravitational potential energy. That is mg into delta H. Okay. Let me just clarify one point here. Suppose this is the ground level. And an object is taken from this height to this height. Assume this point, the initial point, is at an actual height of 3 meters from the ground. And the final point is at an actual height of, let's say, 10 meters from the ground. Let's say object mass is 2 kg. Okay. One of you use the formula and tell me how much is the change in gravitational potential energy as it is taken from A to B.
Sir, mgh2 minus h1.
Substitute and tell me the numerical value. The formula you used is correct only. Substitute, how much will it be?
140, sir.
Okay. 2 into 10, 20 into 7, 140 joules. Fine. Now listen. Here, that 3 meter and 10 meter were written based on the ground as the reference. We took ground as a 0 height. Then from that, based on that, we wrote 3 and 10. But see, while applying mechanical energy conservation, you write initial potential energy on one side, final potential energy on one side. So ultimately in the equation, what matters is the change in potential energy. To do that, you can even consider the initial height as 0, and based on that, the final height becomes 7. Will you get the same answer even now or not? Had you taken 0 and 7 instead of 3 and 10, would you get the same answer or not?
Yes, sir, we will get the same answer.
Okay, others, do you agree with it? You will get the same answer. So what I'm saying is, to calculate gravitational potential energy, okay, you can assume one of the heights from where to where the object goes. An object will be moving, no? You can assume the height anywhere as 0. Because in the mechanical energy conservation equation, you will be writing initial gravitational potential energy and final also. So ultimately in the equation, what you are using is the change in gravitational potential energy. And for change, the initial value, final value don't matter. I mean, yeah, change is calculated based on initial and final only, but the difference will always be the same even if you change both values by the same amount. Like 3 and 10, reduce both of them by 3 units, it becomes 0 and 7. The change is still 7 units. Okay. So when applying mechanical energy conservation, if you have to include gravitational potential energy in the equation, you can assume any one of the levels as 0, 0 energy level. Any level above it will be positive energy, positive potential energy. Any level below it will be negative potential energy. Okay. So you can write gravitational potential energy. Now we are not talking about change. We are talking about the actual value. Gravitational potential energy can be written as mgh, where h is height above the level where you consider potential energy to be 0. So at some level, we'll assume potential energy is 0. If the object is above it, positive height. Object is below it, negative height, you will get the answer. Let's apply that in this problem now. Okay, I'll copy all this. Okay. Now okay, I will tell you to take, I will give you the reference. Assume this height is 0 height. For gravitational potential energy calculations, assume the initial height is 0, then the final height will be minus mg by k because it is below the 0 level. Okay, final height will be minus mg by k. These you can use in gravitational potential energy calculations. Or you could have done it like this also. You could have assumed initial height to be x. We don't know how high it is above the ground, so take it as x. Then the final height will be x minus mg by k. Okay, because the final position is below the initial position, so final height will be x minus mg by k. If you substitute initial gravitational energy, you'll get mgx. Final, you'll get mg into x minus mg by k. That mgx part will get cancelled anyway. So whether you take x as 0, means whether you take that initial height as 0 or some non-zero value is not going to matter. That's what I am effectively trying to say. Okay. Let's substitute the values now. I'll just write the formula. You do the substitution. Okay. These are not, okay, numerical values are not given. Directly from the formula, we'll get the answer. One of you tell me, at position A, which is the initial position, how much is the potential energy stored in the spring? potential energy stored in the spring at initial position. How much is it?
Sir, 0.
Why? 0 is correct. Why is it 0?
Sir, and A మనం ఇనిషియల్ పొజిషన్ కి తీసుకున్నాం కాబట్టి.
No,
And
just
height-
because. See, wait. I'm asking about spring potential energy. Gravitational కాదు. Gravitational depends on height. Spring potential energy depends on deformation of the spring.
సార్ అంటే మనం న్యాచురల్ అని తీసుకున్నాం కదా సార్.
You should give that as the reason. Initially, the spring was at natural length. Therefore, it does not have any potential energy. So the first term becomes 0. Next. One of you tell me, how much is the gravitational potential energy initially? We considered the initial level as 0 height level. Okay. Therefore, gravitational potential energy will be taken 0. Next, kinetic energy. Was the block moving initially? No, it was released from rest. So kinetic energy is also 0. All three are 0 initially. Okay. Now one of you tell me, how will you write? Just tell the formula for final springs potential energy. How will you express the spring potential energy after the block comes down?
సార్ హాఫ్ kx స్క్వేర్.
Half kx square, correct. What will you substitute in place of x? How much is the deformation in the spring?
mg/k.
Correct. So half k into mg/k whole square. Next. Okay, someone else. Aishwarya, you tell. How will you write gravitational potential energy finally? Gravitational potential energy formula is mgh. So you consider the final height and based on that you tell.
Sir, minus m into g into minus mg/k.
See, why will you put 2 minus s? Okay.
Sorry, sir, m into g into minus m.
The formula is mgh. The height here is negative minus mg/k. And the final kinetic energy of the block will be taken as half mv square, where our aim is to calculate v. Okay. What is left is just simplification. Left hand side is 0. Right hand side, first term, k into mg/k whole square is m square g square by k square. 1k will get cancelled. You will be left with half m square g square by k. Second term, plus into minus is minus. Numerator is m square g square. Denominator is k. Third, half m v square. Now you observe the first and second terms. It's half m square g square by k minus m square g. It's like half minus 1. Half minus 1 is minus half. By k. Send it that side, it becomes plus half. Therefore, half m square g square by k is equal to half m v square. Half m gets cancelled. You will get v as g root m by k. And that's the answer we had gotten before also by using work kinetic energy theorem. Okay. So first, basically there is some change happening in a system and speeds are changing. The arrangement is changing and speeds are changing. So we try to apply mechanical energy conservation. We check the conditions on every moving part of the system. In this case, it's the block and spring. What are the forces acting? Spring force and weight. Both are conservative. So there's no chance of non-conservative forces doing work here. So you can apply mechanical energy conservation. And we did that. Okay. But there were two conservative forces doing work this time. In the previous problem, the spring block system was moving horizontally. Because it was moving horizontally, weight was not doing any work. But in this problem, there is vertical motion. So weight is also doing work. Two conservative forces doing work. So two potential energies have to be included in the equation. And kinetic energy, obviously. Okay. Now we solved this by taking the initial height as 0 level and final as minus mg by k. As I said, you could have taken final level 0, initial level as plus mg by k also. It would not make any difference to the equation. In that case, how you'll write? Initial spring energy is 0, gravitational potential energy. Initial height, if you take mg by k and final 0, then initial gravitational potential energy becomes mgh. Kinetic energy is 0. Finally, spring stores potential energy half k x square. Finally, the block came to 0 gravitational energy level. So right hand side gravitational potential energy 0. Kinetic energy half mv square. Solve it, you will get the same answer, g root m by k. Okay, so the thing you need to remember from this problem is that while applying mechanical energy conservation in a problem, it does not matter which level you take as 0 height for gravitational potential energy. That's what you need to understand from this problem. Okay. Let's discuss a much simpler case this time. Assume this is the ground level. A ball is projected with a speed u in the upward direction. Tell me what happens to the ball. Ignore air resistance. What happens to the ball?
Or it goes up. And then after a point, the u becomes 0 and then it starts going down.
Okay, it slows down as it ascends and at some level it stops. Okay, so we know it reaches a maximum height. So let's say this is the maximum height attained by the ball. Where the speed we know becomes 0. Okay. So speed of an object is changing because it is moving. So there is a change in arrangement and there is a change in speed. In fact, to derive H max now, you can use mechanical energy conservation. One of you tell me, what is the reason behind slowing down of the ball? What force makes the ball slow down?
Gravity.
Gravity. Conservative or non-conservative?
Conservative.
Conservative. So what is causing a change in the system is conservative force. Therefore, mechanical energy conservation is applicable. Let's say it ascends by a height h. Okay, some of you may be remembering the formula also. Let it be. Let's say it ascends by a height h, and that is what we need to calculate. So what we are going to do now is initial potential plus kinetic energy is equal to final potential plus kinetic energy. Luckily, there is no spring involved here. So gravitational potential energy is the only potential energy you need to consider. You can assume the initial level as 0. If initial height is 0, final height will be capital H itself, which is what you are trying to calculate. Okay. Now, if the initial level is assumed to be 0 height, tell me how much is the initial potential energy? This is the initial position A. This is the final position B. At the initial position, how much will you write its gravitational potential energy as?
Sir, 0.
0, because we are considering that height as 0. So initial potential energy is 0. Initial kinetic energy is half mu square. Okay. Finally, when it ascends by a height h, since you are considering the final height as h, final potential energy becomes mgh. And kinetic energy there, the ball we know is stopping. So kinetic energy is 0. That's all. Cancel mass. You get u square by 2 is equal to gh, or h is equal to u square by 2g. We had done this derivation earlier using equations of kinematics in the chapter motion in a straight line. But now you understand that it can be derived using mechanical energy conservation also. Okay, because this is a case where an object's motion is affected by conservative forces acting on it. So in any such case, you can apply mechanical energy conservation. Okay. Try another problem. A ball, actually its mass need not be given, but if you need mass in the equations, no? Okay, just a moment. Someone is trying to join the meeting. Okay. So if you need to include mass in the equation, just write it as m. It will get cancelled anyway. Assume a ball is thrown down with an initial speed of some 20 meters per second. Okay, so it's not simply dropped, it is thrown down with some non-zero speed. Okay. The question is to calculate its speed when it falls down or when it descends by 60 meters. Okay, under gravity, air resistance is ignored. Under the influence of gravity, if it descends by 60 meters, calculate its final speed. Okay, solve this quickly. One of you tell me, what makes the speed of the ball change? What makes the speed of the ball change?
Sir, gravity.
Gravity. Conservative, non-conservative?
Conservative.
Therefore, you can apply mechanical energy conservation to solve this problem. So do this all of you. Initial potential energy plus kinetic energy is final potential energy plus kinetic energy. Now, wait, I want to know how you all are solving. Gravity is the only force involved here. So gravitational potential energy is the only potential energy you need to consider. And for gravitational potential energy, you need to assign a height. Okay. So I want your answers this way. What are you taking the initial height as? And what are you taking the final height as? Then, okay, like you answer like this: first, second, then third part. Third part, I think you can give the answer now, finally. Yeah. Type your answers like this in chat. Make it fast, all of you. What happened? I didn't get even one answer. Okay, one answer. 60, 0, and 40. Fine. Listen, to calculate gravitational potential energy, as I said, you can assign any one height as 0. Okay, in the entire situation. Okay, or in the entire diagram, you can assume any level as 0 height. Let's assume the initial height itself is 0. If the initial height is taken as 0, then the final height should be taken minus 60 because final position is below the initial position. You can do it this way. Okay, so let's use these values. Initial height 0, final height minus 60. Based on that, we'll write. Yusuf, tell me the formula for gravitational potential energy. Once you assign the height, how much is, or how do you calculate the energy? No response. Rishi, you tell the formula.
Can you repeat your question?
What is the formula to calculate gravitational potential energy once the heights are assigned?
Uh,
A simple formula for potential energy. Okay, Saket.
Sir, mg delta H.
Listen, again, let me clear this to all of you. Change in gravitational potential energy is mg delta H. Therefore, final gravitational potential energy minus initial gravitational potential energy is mg into final height minus initial height. Now, when we apply mechanical energy conservation, we have the initial term on one side of the equation and final term on the other side of the equation. So keep the initial terms on one side of this equation, final terms on one side. You get final potential energy, or you can say like this. You can take final potential energy as mg into final height and initial potential energy as mg into initial height. Okay, and that is how we are going to substitute in the potential energy, mechanical energy conservation equation. So initial potential energy will be written mg into initial height. Final gravitational potential energy will be written mg into final height. Is this clear to all of you? So remember, formula for gravitational potential energy is mgh only once you assign the heights. Okay, now we are taking initial height to be 0. Therefore, initial gravitational potential energy will be 0. I'll write it properly here, mg into 0. And initial kinetic energy is half m u square. The ball is not simply dropped, it is thrown down with a speed 20 meters per second. So 20 squared is equal to final gravitational potential energy, mg into final height. Final height is minus 60 because it is 60 meters below the initial value. And final kinetic energy, half m v square. V is what we need to calculate. M can be cancelled. Substitute g as 10. The first term is 0 anyway. 20 square is 400 by 2 is 200 is equal to 16 to g is minus 600 plus v square by 2. So 600 this side becomes 800. 2 also this side becomes 1600. Means v square is 1600. That means final speed is 40 meters per second. Okay, this is how you get it by applying mechanical energy conservation. You could have solved this problem using equations of kinematics also. V square minus u square is 2as. Apply it in the vertical direction. You get v square, just a moment. V square minus u square is equal to 2 into acceleration due to gravity is in the downward direction, so minus 10. Displacement is 60 meters downward, so minus 60. 16 to 10, 600. 600 into 2, 1200. V square minus 400 is 1200, means V square is equal to 1600. That will also give you V as 40 meters per second. Okay, but now we did it in a slightly different manner by using mechanical energy conservation. You can do it using work energy theorem also. Gravity is the only force which does work. Gravity is mg. Okay, gravitational force is mg. Height descended is 60 meters. So work done by gravity is mg into 60 is equal to half m final speed square minus initial speed square. Work done by all forces is equal to change in kinetic energy. This way also you will get the answer. Okay, so basically we are learning different techniques that can be applied to solve problems in physics. Okay. Let's try another question. Slightly different situation this time. Assume there's a fixed nail here and a string is attached to it, and at the other end of the string there is a ball or stone, whatever it is. The stone is taken to the position where the string is horizontal. Okay, assume the length of the string is L, mass of the stone is M, and you release it from here from rest. Release it at this position from rest. Can one of you describe what is going to happen? Once you release the stone, what happens? Just a stone connected to a string. You take it to the horizontal position and leave it. What will happen?
Sir, it oscillates.
Sir, the
Oscillates.
mass will oscillate.
Okay. It will come down first, right? It descends. Fine. It oscillates is also correct only, but it starts descending. That much we can tell for sure. Comes to this position at one instant. Like the string will become vertical at one instant. When the string is in this position or when the stone is in this position, can one of you tell me whether it will be moving or it will be at rest? The first time it comes to this position, will it be moving or it will be at rest?
It will move, sir.
It will be moving, okay? Because as it comes down, gravity would have given some speed to the stone. So here it will have some non-zero velocity. And with that velocity only, it goes to the other side. On the other side, ascent will take place. During ascent, the speed will reduce. It will stop somewhere and come back. So from here to here is descent, no? During descent, speed will increase. Okay, so some speed it will have at that position. The problem is to derive that speed. Okay, think of how to solve this. Length of the string is given to you, mass of the block is given to you, mass of the stone. Mass is not necessary, actually, it'll get cancelled. And you know gravity. So think of how to solve this problem. Any ideas? Okay, see, you know the initial speed of the object. And you know from where to where the object is going. So we know, we kind of know the displacement or the change in arrangement. Is known. And you are asked to calculate the final velocity. How can we relate all these? Like which formulas or theorems can we use to relate all these? There are a few things that you can do. One is you can use v square. I mean, if conditions are applicable, if conditions are satisfied, not applicable, satisfied, you may use v square minus u square is 2as. Okay, it's one of the equations which can help you calculate final velocity, like what we did in the last problem. Another thing you can do is work kinetic energy theorem. Work kinetic energy theorem has no conditions. If you can calculate work done by all forces, you can always use it. Okay. And how is this applicable in such situations? Because kinetic energy, like how do you apply work kinetic energy theorem? Work done is change in kinetic energy. So here you will write it as half mv square minus u square. Work done involves displacement. So this is also one of the things which relates displacement to speeds. Okay, so work kinetic energy theorem can be applied to solve such problems, but only if you can find out the work done by all forces and all. And today, last class and today we have discussed something called mechanical energy conservation, but this comes with a condition. Okay, but you can use it. Initial potential energy plus kinetic energy is equal to final potential energy plus kinetic energy. How do we get the idea that such things are, this thing is useful here? Potential energy depends on arrangement. Kinetic energies depend on speeds. And this is a question where arrangement is changing and you are asked to calculate speed. So this also is applicable. Okay, I mean, if conditions are satisfied, this can also be applied. So remember, in any situation where you are asked to find out the speed of a moving object at some position, okay, you know speed at one position and you need speed at some other position, you will try to apply one of these. The question may be asked the other way around also. You can be given speeds at two different positions and asked how far the object goes. Then also you can try to apply one of these. Okay, so speeds and arrangement based questions, these are the things that you will try. Okay, two of them have conditions. The middle one doesn't have any condition. So which one you apply depends on which you are comfortable with and which one's conditions are satisfied. One of you tell me, as the stone moves, do you think its acceleration will be constant? Do you think the acceleration of the stone will be constant as it moves? Because if it is constant only, you can apply equations of kinematics. That's why I'm asking you. The question was if the acceleration is constant. Acceleration is based on forces. Think in terms of forces. At least tell me this. As the stone moves down, what forces act on the stone at any instant?
Sir, mg and then tension.
Gravity and tension, correct. Weight, gravity, is a constant force. So maybe acceleration could be constant, because if gravity was the only force acting, acceleration would have been constant. That's how we answered the last problem, no? I told you it could be solved using equations of kinematics also. Okay. But tension is also acting here. Tell me, as the stone moves down, is tension a constant force or a variable force? We had talked about this before also.
Variable force, sir.
Variable force. On what basis are you saying it is variable? How did you decide it is variable? Its direction is changing. Actually, magnitude also will be changing. Direction is definitely changing. So tension is a variable force here. And if force is variable, acceleration will be variable. There's no guarantee that equations of kinematics are applicable now. So we won't use this. Work energy theorem can always be used. You need to know work done by weight and work done by tension, because those are the two forces acting here applicable. Mechanical energy conservation also we'll see. We'll solve it using all the methods that are applicable here. Equations of kinematics is not applicable, that we have concluded. Okay, let's try to use work kinetic energy theorem. Okay, follow me carefully, all of you. You know the forces acting are tension and gravity. Can any of you tell me how much will be the work done by weight in this process? Weight is a constant force, you can take advantage of that. How much is the work done by weight as the stone descends?
mgl, sir.
Okay, okay. Aishwarya, can you tell the formula for work done by a constant force?
Sir, F into S.
Don't use
F
the
dot
word
S.
yeah, F dot S, Fs cos theta. Okay. Vanilla, your answer is correct only. See, Fs cos theta is the work done by a constant force. The force we are talking about here is mg. Aishwarya, how much is the displacement S? Or can you tell S cos theta at least? Weight is a constant force. We are using Fs cos theta to calculate the work. Force is mg. What about S and cos theta? Okay. If you visualize, the actual displacement of the object is from here to here. This is the total displacement. And gravity acts vertically downward like this. At every instant, it's like this only. So this is the angle we are interested in. Like from geometry, you can tell, like since this angle is 90 degrees, this will be 45. L and L displacement will be L root 2 hypotenuse. You can do all that, but not necessary. You don't have to do so much calculation just to find out work done by gravity. Gravity is a force in the downward direction. And we know that in the calculation of work done, S cos theta, like after you multiply them, you effectively get displacement in the direction of force. Now here the actual displacement is slant, let it be. But in the direction of mg, what is the displacement is what matters. And let's visualize that. It is descending, mg is in the downward direction, no? So in downward, how much it has moved is what we want. And that is nothing but L. It came from this level to this level. So the displacement in the vertical direction is L itself, downwards. Okay. So the work done by gravity will be the force mg multiplied with the displacement in the direction of the force is L. So work done by gravity is mgl. Okay, we got work done by one of the forces. The next force acting is tension. The other force acting is tension. This also we had discussed before, but if you remember, you tell, otherwise think and answer. As the stone moves from position A to position B, how much is the work done by tension? If you cannot calculate, you tell you cannot calculate.
Zero, sir.
Good. Why is it 0?
Sir, tension is perpendicular to the velocity always.
Okay. See, we know tension is a variable force in this case. Listen to this carefully, all of you. These situations are quite common. We know tension is a variable force. And work done by variable force is calculated as integral that force dot small displacement. Now, as the stone moves down, okay, just a moment, I'll copy the diagram. As the stone moves down, at any moment, okay, at a random instant, if you consider, tension acting on the stone will be along the length of the string, like this. Whereas the displacement at that moment will be tangential to the path, like this. Since these two are in perpendicular directions, their dot product will become 0 always. So the dot product is 0 and integral 0 is 0 itself. Therefore, tension does not do any work as the stone descends. On the other side, when it ascends also, tension won't do any work. Now the problem is almost solved. We got work done by weight and we got work done by tension. Means we got work done by all the forces. Initial velocity of the block was 0. Final velocity is what we want. Total work done is equal to change in kinetic energy. That means work done by weight plus work done by tension is equal to half mv square minus half mu square. That's all. Mass gets cancelled, you get V as under root 2 GL. So we solved this problem using work kinetic energy theorem. Okay, can be done. There was another way also, we thought maybe we could do it. Okay, work kinetic energy theorem gave us the answer. The third method we considered was mechanical energy conservation. Quickly tell me the condition for mechanical energy conservation. Make it fast. Vanilla, don't answer.
Work done by non-conservative forces must be equal to 0.
Work done by non-conservative forces must be 0. Now, as this stone moves down from position A to position B, what's the only force which is doing work on it?
mg.
Weight. Okay. There were two forces acting on it, weight and tension. We concluded tension does not do any work. So weight is the only force doing work. And is it conservative or non-conservative? Gravity.
Conservative.
Conservative. So this method is also applicable. Let's try this. Okay, let's solve it this way also, using mechanical energy conservation. And the conservative force involved here is only weight. So gravitational potential energy should be considered. Let's do that. How do we apply mechanical energy conservation? Initial potential energy plus initial kinetic energy is final potential energy plus final kinetic energy. Now we are talking about gravitational potential energy. The formula is mgh, but the formula is mgh after you assign the heights. It's your choice which level you take as 0. I'm going to take the final level as 0 now. Okay, as I said, it's our choice. I'll take this as 0 height. Then the initial height will be L. Okay, because it is plus L, because it is at a level L above the 0 level. So initial potential energy will be written mg into initial height, that is mgl. Initial kinetic energy is 0 because stone was not moving. Finally, when it is at the bottommost position, potential energy becomes 0 because that level was taken as 0 height. So mg into 0, I'll write it as mg into 0. Plus final kinetic energy half m v square. This term is 0 anyway. Mass gets cancelled. GL is equal to half v square. So v square is 2GL, v is under root 2GL. Even this way you get the same answer as expected. Why will the answer change? Okay. See, what you are learning in these classes is very important. Like this class and the next few classes. You are learning ways to calculate speeds based on displacements. Okay, in some of the problems following, we'll do the reverse also. You'll be given initial speed and asked how far it goes, or you'll be given initial speed and asked how far it goes by the time its speed becomes some other value. So final speed also will be given. Such situations. And remember, there are 3 ideas you can use to solve problems like this: equations of kinematics, work energy theorem, mechanical energy conservation. Equations of kinematics and mechanical energy conservation come with conditions. If condition is satisfied, you can use. Work energy theorem has no condition. You can always apply if you are able to find out work done by all the forces. Okay, so let's quickly recollect what all we discussed today. First, we just considered an example where a non-conservative force, that is friction, removes mechanical energy from a system or changes the mechanism. That's the idea behind mechanical energy conservation. Conservative forces cannot disturb mechanical energy. Non-conservative forces can add or remove mechanical energy from a system. If non-conservative forces do positive work, mechanical energy increases. If they do negative work, mechanical energy decreases. One of those can happen. So we just looked at a block sliding on the ground case. Friction removes mechanical energy from the block. Then elastic potential energy of a spring. See, the last worksheet that I sent is compulsory. Solve it and send. Okay, you have to derive this formula for potential energy stored in a spring. The steps are clearly given in the worksheet. Follow all the steps. I mean, write answers to each question. You will get this result finally. So gravitational potential energy changes are calculated like this. Spring potential energy is calculated like this. then we kind of derived law of conservation of mechanical energy using work kinetic energy theorem. Work done by all forces is change in kinetic energy. And if work done by all forces is only the work done by conservative forces, then this term becomes negative of change in potential energy. Okay, so negative of change in potential energy is equal to change in kinetic energy, means sum of change in potential and kinetic is 0, means total change in mechanical energy is 0. That is what is mechanical energy conservation. Okay, then we discussed cases where it is applicable. Spring block system, we had solved this question earlier, we did it again today, we got the same answer. But today we solved it using a different method, mechanical energy conservation. This question also we had solved in the last class, we did it again today. Mechanical energy conservation gave us the same answer. And then these last two problems, fine. So solve the worksheet that I had sent you, the last worksheet that I had sent you. And tomorrow also you will get one worksheet having questions based on mechanical energy conservation. I'll give you 5 questions. You have to give some time and carefully apply all this because these are very important concepts in physics. These are some of the most basic concepts in physics. Okay, thank you all. We'll continue on Wednesday. And Wednesday also class will be, okay, I'll inform the timings. By tomorrow
you, sir.
morning, I'll inform. Okay, thank you all.